Hello everyone, it's Mr. Spinelli, and today we're going to talk about rewriting integrals using summation notation. Now I'm just going to hit you with all the formulas right up front, so maybe pause the video, write all this down, and I'm going to explain what all these different pieces mean. So the first thing we notice is we want to rewrite the integral of f of x with respect to x from a to b. So this is a definite integral, and we're rewriting it as the limit of a summation. So this symbol here, this sigma, is a summation. I'm going to operate under the impression that most of you know what this is. Otherwise, stick around towards the end of this video and I'll dive more into the nitty-gritty details of that. But what I'm doing is I'm plugging in the lower index, I equals 1, in for I, which you see x sub I here. So I plug in 1, evaluate what f of x sub 1 is, times delta x. Delta x here represents the width of a rectangle, okay, and f of x sub I represents the particular height of a rectangle. Now I plug it in for however many rectangles I have from I equals 1 up to n being the number of rectangles, and then ultimately with an integral I want to make the rectangles infinitesimally small in their width so that I can fill up the entire space with infinitely many rectangles, which will give me the exact value of the area under the curve, which is represented by this integral. Now x sub I, all you need to notice is that it starts at a, which is the lower index of your limit of integration, and we add I times the width. Remember, delta x is the width, and I is just a counting number. And we'll look at an example and see where that I comes into play later. And delta x, the width, is just b minus a, where b is the upper limit of integration and a is the lower limit of integration, divided by n, where n is the number of rectangles. And remember again, ultimately we take the limit as n goes to infinity because we need infinitely many rectangles that are infinitesimally small in their width. So then ultimately this formula at the bottom is just what you get when you plug in all of the information for x sub I and delta x. So what AP typically wants you to do is to be able to write the limit of a sum given an integral, or write the integral given the limit of a sum. So we're just going to look at some examples before we kind of do one on our own and just see what kind of patterns we notice. So here is just a smorgasbord of limits of summations that represent the integrals that are given on the left. So the first thing we're going to notice is the bounds, the limits of our integration. So the first one goes from 0 to 4. Now remember my formula for x sub I, this is key for figuring out how to write these. X sub I is equal to a plus I times delta x. And remember, delta x is just the difference between b and a, which in this case is 4, divided by n, which is the number of rectangles you're going to have. So the thing that I would maybe look for is the x sub I. So if we compare these first two problems, the first one starts at 0, the second one starts at 1. But they both have a difference of their lower and upper limits of integration of 4. 4 minus 0 is 4, and 5 minus 1 is 4. So you'll notice in both problems that they have this 4I over n. That's me adding the increment from my I times delta x. And then you'll see that 4 over n again on the outside because that's the width. And you'll see that throughout all these problems, width. I'm just going to write W, width. But then on the inside, I'm evaluating the height. So everything that I put inside the brackets, that is the height of each individual rectangle. And it's simply given by plugging this x sub I into my function, whatever my integrand is in my integral. So in this case, I replace x with this formula, a plus I delta x. Now in this case, the first one, a is 0. That's why you don't see me adding anything. But in the second one, you'll notice that my starting value is 1, so I've added 1. That's the only difference between these first two problems. And now in all of these problems, I'm doing the limit as n goes to infinity of the summation of from I equals 1 to n. Uh, and we'll get more into the details of what all this means later, but ultimately you just got to recognize how to write these and how to match them together and things like that. So now let's scroll down just a little bit. Let's leave it there actually. So in this third one, you'll notice again we're going from 0 to 4, so every single thing is the same as that very first problem. The only thing that's changed is the function that we're integrating. We're no longer integrating the square root of x squared plus 9. It's just x squared plus 9. So you'll notice that the square root from the first two problems is no longer there. That's all that changes. Now in the fourth problem, you'll notice that it goes from 1 to 3. Well, the distance from 1 to 3 is 2, so now that's why you see 2I over n and 2 over n. So that 2 over n comes from the delta x. 3 minus 1 is 2, divided by n, the number of rectangles you're going to have, and then the I comes in because of this formula x sub I. That I is like a counter for us. And then again on the fourth one, we start at 1, which is why we've got an additional 1 plus for where we replaced x. Alright, scroll down a little bit more and look at the rest of these. We'll save that last one. Okay, and the next one, now my function's just changed. Now it's 2x plus 9. I'm again going from 0 to 4. Okay, so I've got 4 over n is my width, my delta x. 4 over n times I is my additional counter to get to my next point. And now it's 2x plus n, which is why you see 2 parentheses, my x sub I, and then plus 9. And then on the very last one, the only thing that changed is now we're starting at negative 1. So now we've got a negative 1 starting point. I still have a width of 4 over n, and everything else remains the same. So then just as a little counterexample of something that's different than what you've been seeing, we'll write out some of the details on this one. So I'm going to write out what delta x is. Pretend like I didn't have what's on the right. So my delta x, I take my 11 minus 7, my upper limit minus my lower limit of integration, divide that by n, so that becomes 4 over n. Well, you're used to seeing that 4 over n. We've seen that several times now. So here's my 4i over n for that counter, and 4 over n for my width. And then I just need to remember where I start. So on this one, I'm starting at 7, and that's why wherever I see an x in my original integral, I replace x with what x sub I is. And x sub I is simply my starting value a plus I times delta x. And that ultimately just becomes 7 plus 4i over n. And at the very end of this, we will do a random example that I will make up on the fly. But let's dive into the fun stuff, the old stuff, things you know how to do. And we're going to connect it to what you just saw. So this first one says, estimate the value of the integral using a right Riemann sum with 2 equal subintervals. So I'm going to note here that 2 equals, so I'm going with n equals 2. I'm going to use all of the same formulas, but I'm going to pretend like we don't even know what those formulas are for now. So you guys have done right Riemann sums. Okay, right Riemann sums. I need to figure out how many intervals I have and where those intervals are going to be. So I like to go old school. I'm going from 3 to 15 for my integral. I want to know what that distance currently is. That distance is 12. Well, if I want to divide that into 2 equal pieces, I know that those distances are going to be 6 and 6 respectively, because they got to be the same, which means I'm adding 6 to 3, which gives me 9. Now, I got 3 points that are defining these 2 equal subintervals. I'm always going to have n plus 1 number of points. But since I'm using a right Riemann sum, I'm really only going to use the 9 and the 15. Now, as you know, what I'm going to do is I'm going to multiply the widths of these rectangles. If I were to actually draw a rectangle, I will leave that exercise to you. But ultimately, I'm going to multiply the width, which is 6, times the value of the function evaluated at those 2 points, 9 and 15. So I'm going to do 3 times 9 squared minus 5. And then I'm going to add another 6 for the width of the second rectangle. And it's going to be 3 times 15 squared minus 5. And this would give me the estimate of the value of this integral using two equal subintervals. Now, I will leave the math exercise to you of plugging this into your calculator, but you should get 5,448. Now, those of you that are smart know that this value can easily be computed exactly. You know this is going to be x cubed minus 5x evaluated from x equals 3 to 15, which the exact value of this integral is 3,288. Now, our estimate, using only two subintervals, right Riemann sums, which you should know why that's an overestimate. Take a look at the concavity or the first derivative. I'll let you determine, based on your notes, what you should be looking at. Hint, hint, hint. That's what this thing looks like. So we clearly have an overestimation. Now let's rewind the tape. Let's go back to the formulas that I gave you. I told you that the formula for x sub I was a plus I times delta x. Well, what's our a value here? We start at 3. Our delta x is simply 15 minus 3 divided by n, and this all gets multiplied by I. Well, that's really just 12 for that 15 minus 3, but my n value is 2. So I end up with 3 plus 6i. Well, since I'm using two equal subintervals with right Riemann sums, my x sub 1, if I plug 1 in, I get 3 plus 6 times 1, which gives me 9. 9 was the first point that I used. Well, what was x sub 2? X sub 2 was 3 plus 6. Now I replace the I with a 2, and I get 15. 15 was the second endpoint I used. And my formula said that I used the sum from I equals 1 to n, in this case n is 2, of f of x sub I times delta x. Well, my delta x for all of this was simply 6. So replacing delta x equals 6 and using these x sub 1 and x sub 2's for this formula here, this gives me this number that we just computed. Now notice this doesn't involve a limit because I only did a finite number of subintervals. I didn't take the limit as n goes to infinity. We'll do that in a moment. So then, let's take a look at with n equals 4. So, without further ado, we bust out the 3, we go all the way to 15. We know that distance is 12 divided by the 4 equal subintervals for a right Riemann sum. I'm going to be looking at distances of 3 to separate all these points. So I'm going to have a point at 6, 9, and 12. Okay, so I'm kind of cutting out some of the details from before because you've seen it once, you can see it again. Right Riemann sums, I'm taking the 4 points from the right. I should really start from the 15 and work my way over to the 6, but you guys should be comfortable with that. And then what do I do? Well, my formula says I do the sum from I equals 1 to n, in this case n is 4, of f of x sub I times delta x. Well, what's my x sub I? My x sub I formula says it would be 3 plus 12 over 4 now gives me 3, so it's 3 plus 3i. So x sub 1, 2, 3, and 4, this probably isn't the most appropriate way to write it, gave me the 6, 9, 12, and 15. And as you know, delta x is simply 3 because that's the distance between any of these points. All these are the same for delta x. Okay, so delta x was equal to 3. Now I plug in my formula, and this simply gives me width of 3 is going to be applied to all of these, so I'm just going to put a big old bracket 3 outside. So I'm going to do 3 times 6 squared minus 5. That's my first point, plus 3 times 9 squared minus 5. That's for my second interval, plus 3 times 12 squared minus 5. And my last interval is 3 times 15 squared minus 5. So this should all be review. Plug this into your calculator, and you get 4,314, which is still significantly overestimating the exact answer of 3,288. So now, let's dive into the details of what would happen if we did n equal subintervals. Well, let's just start off by using our formulas. So x sub I, in this case, is going to be 3 plus 12 over n times I. Where did I get the 12 over n? I got it from delta x being 15 minus 3 divided by n, which is 12 over n. So these are the two things I need to rewrite this definite integral as the limit of a summation. So this is going to be precisely equal to the limit as n goes to infinity of 3. Now I've encountered an x. I have to replace, I already forgot my summation. Limit as n goes to infinity, the summation of I equals 1 to n of, now my function, f of x sub I. Well, f of x is 3. I replace x sub I, or x with x sub I, which becomes 3 plus 12i over n. I square that, and I subtract 5. So this right here, which I'm going to put in brackets, is my f of x sub I. F of x sub I, recall, represents the height of a given rectangle. And I multiply that by the width, which is 12 over n. So 12 over n represents the width of a given rectangle. Now, you don't need to know how to do this, but I'm really curious, what on earth does this actually mean? Let's do the math. Let's actually expand this and compute the limit of this summation to show why this really works. Because remember, the goal is to show that this actually does equal the 3,288, which is the exact value of this integral. So, with some multiplication, which I am going to leave to you to verify, because you've got to square that polynomial and then distribute the 3 to it, you're going to end up with 22. I can tell you right now that comes from the 3 being squared and then multiplied by the 3 out front of that polynomial squared minus 5. So 3 squared is 9 times 3 is 27 minus 5 gives you 22. Then you're going to have plus 216i over n plus 432i squared over n squared. And then all of this is still going to be multiplied by that 12 over n on the outside. So what I'm telling you is that there's some algebra steps to be taken care of in between here. I would invite you to practice that. That's good for your algebra skills. Now I'm going to distribute the 12n to everything. So I'm going to multiply all of these terms in here by 12n. I end up with the limit as n goes to infinity, the summation from I equals 1 to n of 264 over n plus 2,592i over n squared plus 5,184i squared over n cubed, and drop the mic. But we're not even close to done. Now there's some important properties of summations that I just don't have the time to cover every single one of them. But because I'm doing a summation with an index of I, that is, I'm changing I, I'm going to plug in 1 for I, then I'm going to plug in 2, then I'm going to plug in 3, etc., all the way to infinity, and then I'm going to add all of those things up. Well, I simply don't have the time to add up infinitely many things. So, one thing I can do is factor out anything that doesn't involve an I. And I can also split this up to be three separate sums because I have three terms being added together. So with a rewrite, I can pull out the 264 over n. Well, let's rewrite the limit. Limit n goes to infinity. So I'm going to just do a big old bracket because now I'm going to write three separate summations. So for this first term, 264 over n, neither of those things has an I. So I can pull them out of the summation. And what I'm really left with is just the summation of 1. Then I have plus 2,592 over n squared, but now I still have the pesky I on the inside. And for the last term, I'm just going to have an I squared on the inside of the summation. But I can pull out the n cubed. So all I did was split this into three separate summations because that's one of the properties of summations, is that the sum of, let's just say, a plus b is equal to the sum of a plus the sum of b. That's just a basic property. You can look up how that's proved. So now, the question is, what on earth is the sum of 1 as I go from 1 to n? Well, what I'm going to end up doing is adding 1 to itself n times. Well, 1 plus 1 n times is just n. So now this first term just becomes 264 over n times n, which, as you know, those n's are going to simplify to 1, and it's just going to be 264. But we'll get there later. Now, the sum of I, there's a formula for that, and I'll dive into that later. But let's just take me for my word that this is what it is. So I get the 2,592 over n squared, and one way to write the sum of I is n squared plus n over 2. Now I have 5,184 over n cubed, and I've got to compute the sum of I squared. That means I'm doing 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared, all the way up to n squared. And when I do that, I end up with 2n cubed plus 3n squared plus n over 6. Ooh, I don't know what I just did. It's some magic. All right. So there I have rewritten everything, and I have told you to take my word on it. You should be good on the first one. If I add up 1 n times, I just get n. If I add up I get this result. Gauss supposedly did this in elementary school, so you might be able to figure that one out on your own. And the sum of I squared can be written as this. So I'm telling you to take those things for granted, or prove them yourselves, or wait later for me to show you. Now, I'm taking the limit as n goes to infinity. So here's the fun part. You all are excellent at taking the limit. This first part we know is just going to be 264 because the n over n reduces to 1. So I get 264. Now this next one, when I take the limit, I notice that I've got an n squared as my degree on top, highest power, and n squared is my highest power on bottom. Well, those are just going to go to 1 over 1 times the 2,592 over 2, which if I simplify that, I won't bother. I'll just write it exactly as you see it, and I'll let you simplify later. Gives you that. Plus, now the next one, I notice that I have an n cubed on top and an n cubed on bottom, so I'm going to go to the coefficient of those two. Well, I got the 2 and the 6 and the 5,184. So 5,184 times 2/6, which is really just 5,184 over 3. Now, I invite you to type these three things in your calculator, and I'm going to take my time as you do it. And what you will find is that it equals exactly 3,288, which is the exact result we were looking for. Okay? So there's a lot of information here, and I just wanted to show you that it all isn't hoodoo magic. And if you stay tuned for another video, I will show you where these three formulas come from. But just for grins and giggles, let's do one more problem together. So I want you to rewrite as a limit of a summation the integral from, let's say, -3 to 7 of x squared minus x plus cosine of x. And I don't know why things are disappearing. This is rather peculiar. Dx. So rewrite that as a summation. So you should probably pause the video and wait for me to give you the answer. And I'm going to give you the answer. So x sub I, recall, is equal to a plus I times delta x, or delta x times I. Multiplication is commutative. And delta x is equal to b minus a over n, which is simply 7 minus -3 over n. So that gives me 10 over n, which, plugging that in down here to x sub I, gives me -3 plus 10I over n. So I'm just multiplying 10 over n times I. I can throw that I on top in the numerator as well. So now I need to rewrite as a limit as n goes to infinity, because I want infinitely many rectangles that are infinitesimally small in their width. I do the limit of the summation from I equals 1 to n. Remember, n is going to be ultimately taken to infinity from a limit of f of x sub I. So I need to replace x squared with -3 plus 10I over n, square it, minus x. I replace x with -3 plus 10I over n, plus the cosine of x. I replace x with x sub I, which is -3 plus 10I over n. All of that is being summed. That ultimately gives me my height, and I multiply that by the width. And I politely drop my pen after I denote that this is the height of a given rectangle, and this is the width. And that's all you got to do to rewrite definite integrals as the limit of a summation. Thank you for watching. Have a wonderful day.